محمد وعلى آله وصحبه أجمعين. This is the second and the last part of section 3.3. In the previous part, we studied coefficient of variation and the empirical rule. We mentioned that for the empirical rule, there are certain percentages in certain intervals, in different intervals, if the distribution is bell-shaped. Now the question, so the empirical rule applies when a distribution is bell-shaped. The question, what if the distribution is not bell-shaped? So we cannot use the empirical rule. Okay, is there any other rule that we can use? What about the many situations in which a distribution is skewed to the right, skewed to the left, not bell-shaped? Okay, so what to do? Well, in these cases, we can use Chebyshev's theorem. So when can we use Chebyshev's theorem? The answer to this question is always. We can use Chebyshev's theorem always with any distribution. Chebyshev's theorem is always true, regardless of how data are distributed. Okay, regardless the shape of the distribution, Chebyshev's theorem is always correct. Okay, don't forget this. While empirical rule is correct only, okay, is used only if the distribution is bell-shaped. Chebyshev's theorem can be used with any distribution, and that's why it is conservative. If you want to find a rule that works with all cases, it has to be conservative. It has to take care of all situations of very skewed to the left distributions, very skewed to the right distributions, all kinds of distributions. What does it say? It says at least 1 minus 1 over k square of the values will fall within k standard deviations of the mean. So that's the formula, at least 1 minus 1 over k square of the values. So it gives you here a formula, not a percentage. Okay, he doesn't say like the empirical rule, approximately 68, approximately. No, there is no percentages. He gives you a formula, 1 minus 1 over k square. So you can use this formula if k is 1, or if k is 2, or if k is 3, or if k is 3.5, or if k is 2.1, or if k is 5.6. Okay, for any value of k. What is k? The number of standard deviations from the mean. So if you replace k by 1, you have 1 minus 0, so at least 0. No information is given. At least 0, okay, at least 0. Of course, at least 0. It should be greater than 0 in the first interval. So nothing, no information in the first interval. Okay, in the second interval, it gives you at least 75%. Why? Because 1 minus 1 over 2 square is 1 minus 1 over 4, 3 over 4. So 75% at least. What is the meaning of at least? It means you could find 80% in the second interval. You could find 90%. You could find 100% in the second interval. We don't know. We know only that at least 75%. It means you will never, for any distribution, you will never find less than 75% in the second interval. 74 is not possible. At least 75 or more. In the third, you can find 89. If you go 3.5 standard deviations from the mean, if this is a mu 1, 2, 3, and you go mu plus 3.5 sigma, and 1, 2, 3, and you go mu minus 3.5 sigma, okay? So you can find the percentage, simply 1 minus 1 over 3.5 square. Okay, use the calculator to find the answer. Then you get the proportion. This is the proportion, which is 0.918. So 0.918 of the data would be between 3.5 standard deviations to the right and to the left of the mean. Or if you change it to percentage, 91.8% of the data will lie within 3.5 standard deviations from the mean. Okay, and you can find the percentage for any k. So this is one difference between the empirical rule and the Chebyshev's theorem. Here you can find it for any k. In the empirical rule, you have only 3 values, 1, 2, 3. If I ask you about 1.5, you say, I don't know. If the distribution is bell-shaped, you don't use the empirical. Then you say it is bell-shaped, but I don't have any number for 1.5, so I will use Chebyshev's theorem maybe to give you at least what I know at least. Okay. So this is one difference. The other important difference, the bell-shaped is symmetric. The distribution here need not to be symmetric. Actually, you have to assume that it's not symmetric. It could be very skewed to the left or skewed to the right. So if 92% are in this interval, don't say half of them here and half of them here. It's not correct. We don't know. We don't know how many of them are here, how many of them are here. We don't know simply because we don't know the distribution, the shape of the distribution. Okay, so the only information I know that at least 91.8% would be in this interval. Okay, what if he asks you about this interval? Okay, if at least 91.8% are here, what would be here? Okay, what would be here? And you cannot say really anything. What you can say, you find the difference, 100 minus 91.8, so 8.2%. So you can say, at most 8.2% are greater than, above mu plus 3.5 sigma, or less than mu minus 3.5 sigma. So this is all what I know. If at least is here, at most would be outside. At least it means it could be greater than, it could be 95. So if 95% here, 5% would be here. Okay, so it is at most 8%. It could be less. Let us solve some questions. A population of unknown shape has a mean of 3,000. This is the mean of the population, which is mu. A standard deviation of the population is sigma. Find the minimum proportion. Minimum immediately Chebyshev's theorem, because Chebyshev's theorem gives you at least the minimum. Unknown shape. If you know the shape, you use the empirical rule, but I don't know the shape, so I have to use Chebyshev's theorem. Find the minimum proportion of observations in the population that are in this range. So you have 3,000 in the middle, and you know that 200 is the standard deviation, and you go standard deviation, the unit of measure is standard deviation. So you go one standard deviation to the right, you reach 3,200. You go another standard deviation to the right, you go 3,000, you reach 3,400. So 3,400 is actually mu plus 2 sigma. So k here is 2. Okay, this k here is 2. Also, if you go to the left, subtract 200, so 2,800, another 200, 2,600. So actually 2,600 is mu minus 2 sigma, and the distance from here to here is also 2. Okay, this is if you want to use the graph. If you want to use a formula, you know the formula. K is the number 3,400 minus the mean 3,000 over the standard deviation, which is 200. The answer would be 2. So what does this mean? 3,400 is 2 standard deviations to the right of the mean. That's the meaning of this. Okay, what about 2,600? If you subtract from the mean, divide by the standard deviation, you find -2. So this means that 2,600 is two standard deviations to the left of the mean. So the question, what is the minimum proportion here? Okay, so k is 2, so I can use the formula 1 minus 2 square, 1 minus 1 over 4, or 3 over 4. So the minimum proportion 0.75. At least 0.75 of observations are in the range or between 2,600 and 3,400. You can memorize these two numbers, 75%, 89%, or you can find them by replacing k by 2 and k by 3. Okay, determine the maximum proportion of the observations that are above 3,600. Well, 3,600, if this is 3,000, 3,600 actually k is 3, because k would be 3,600 minus 3,000 over 200, the standard deviation, and this is 3. So 3,600 is above, is to the right of the mean by 3 standard deviations. He is asking, determine the maximum proportion above. Above means here. So what percentage of the data are greater than 3,600? I have the information. Chebyshev's theorem says to me that if you go 3 standard deviation here and here, then at least 89%, okay, or 0.89, at least 0.89. So what about to the right of 3,600 or to the left of the number here? I have nothing to say except I will say if at least 0.89, at least 0.89, so I will say at most 0.11, which is 1 minus 0.89, at most 0.11 of observations are above or greater than 3,600. And notice that I said 0.11 are above 3,600. Yeah, because it is not symmetric. I don't know how many of these would be here. Maybe all of them would be here in this region. But this is what I can say. At most 0.11 of the observations are above 3,600. Also here for part C, what statement could you make concerning the proportion of observations that are smaller than 2,400? Actually, 2,400 is here because also the difference is 3, k is 3. You can find it. You will find that k in this case is -3. So he needs it to smaller than. So I can also say at most 0.11 of observations are smaller than 2,400. This is all what I can say here. Okay, another question. Consider the following set of sample data. So this is a sample. compute the mean and the standard deviation. Let us use the mean and the standard, the calculator to calculate the mean and the standard deviation. If you put the numbers inside the calculator as we learn and use shift 1 to find x bar, you will find that x bar is 106.2, and s, remember, you need to find the sample standard deviation, not the population standard deviation. So for the sample standard deviation, you need to use number 4, Sx, not sigma x. So S is 25.01. So this is the mean and the standard deviation using the calculator. Calculate the coefficient of variation, CV by definition is S, which is 25.01 over X bar, which is 106.2 times 100%. You calculate this by the calculator and write the answer. This is the coefficient of variation, 23.55%. Now look to part C. Using Chebyshev's theorem, determine the range of values that should include at least 89%. If you look here, 89% means K is 3. So this is the range he is talking about. So 89% means K equals to 3, and means that the range is mu minus 3 sigma and mu plus 3 sigma. So to find this range, mu is 106.2 minus 3 times 25.01, the standard deviation. This is the left, and the right end of the interval, 106.2 plus 3 times 25.01. So you get the following numbers. This is the range, okay, times 25.01. So 31.17, and you change the minus to plus and write the answer. The answer would be 181.23. This is the range using Chebyshev's theorem. Okay, so this is the answer to this part. Now look here. He says what? Count the number of data values. So go to the data and count the number of values that fall into this range. Okay, so how many are there of the data between 31 and 181? And comment on whether your interval is conservative or not. So let us go to the data, see how many of them are between 31 and 181. 31, 31, 62 is the minimum. So all of them are greater than 31. 181, the maximum is 143. 181 is greater than 143. So this means that all the data, all the numbers fall in this range. So actually 14 numbers, if you count them, they are 14 numbers. 14 numbers belong to this interval. Okay, what does this mean? Empirical Chebyshev's theorem says at least 89%. Okay, now we found 100% of the data in this interval. Okay, 100% in this interval. Is Chebyshev's theorem correct? Of course, because it says at least 89. You could have more. We had more. We had 8%. So that's why he says it is conservative. It has to deal with all kinds of distributions. So it would give you the minimum. Okay, but put in your mind you could have more than that in the actual measurements. Another question. The results of a national survey showed that on average, adults sleep 6.9 hours. So this is mu. This is a national survey population per night. Suppose that the standard deviation sigma is 1.2. Calculate the percentage of individuals who sleep between 4.5 and 9.3. So let us find K. What is K for 9.3? I subtract 9.3 minus 6.9. I divide by 1.2. If you use the calculator, you find it 2. Also, if you find K for 4.5 minus 6.9 over 1.2, you will find that the answer is negative 2. So these two numbers, or this range, is 2 standard deviations from the mean. So to find the answer, of course, he said calculate the percentage. I'm using Chebyshev's theorem. Why? Because he did not say the shape of the distribution is mound-shaped. So I cannot use empirical rule. I have to use Chebyshev's theorem. So I say that at least the percentage, at least 75% of individuals sleep between 4.5 and 9.3 hours. Remember, he can here, he doesn't have to give you 4.5. Okay, you could find K 2.5, 2.3, negative 2.5. Okay, you could find K 2.5. This is negative 2.5. You use the formula 1 minus 1 over 2.5 square, and you find the percentage. Now the next point, the standardized data values. This is the last thing. This is nothing new. In fact, it is the number of standard deviations a value is from the mean. And in fact, this is the K we were evaluating in the empirical rule and in Chebyshev's theorem. Number of standard deviations. How many standard deviations a value is from the mean? So it is the K we are finding. We will give it a name. We will call it Z. Okay. So it is the Z value. We will call it the Z value or the standard score. It is called the Z value or the standard score of X. The number of standard deviations, X is from mu. Okay, so X is 2 standard deviations to the right of mu. X is 3 standard deviations, then Z would be 3 or 2. So imagine that Z would be 0 if you are talking about the mean. Okay, at the mean, Z is 0 because mu minus mu is 0. But if your score is greater than the mean, you will start getting some positive numbers, 1, 2, 3. Negative 1 to the left. If your score is negative, if you change it to the standard score and your standard score is negative, it means your score is to the left of the mean. So if you score at Z equals to 3, this means what? It means your score is 3 standard deviations higher from the mean. Really, you could be the best score in the class, because we know that using the empirical rule, almost all the data between negative 3 and 3, if it is bell-shaped. If you scored 3 standard deviations to the right, this means it could be the best score in the class. Of course, if you use the sample notations, you put X bar and S instead of mu and sigma. Okay. This is a question. The mean time that a certain model of light bulb will last is 400. He did not say a sample. So this is a population, 400. Standard deviation, sigma. Calculate the standardized value for a light bulb that lasts 500 hours. So X is 500. And to find the standardized value, this is the Z score. So Z score is X minus mu over sigma, or 500 minus 400 over 50, which is 2. So 500 is 2 standard deviations from the mean. Assuming that the distribution of hours that light bulbs last is bell-shaped, all right, what percentage of bulbs could be expected to last longer than 500 hours? Okay, to answer this question, we use mound-shaped empirical rule. He said bell-shaped. By the way, bell-shaped or mound-shaped, the same. Okay, so he said 500. We found that 500 is 2 standard deviations from the mean. So it is at mu plus 2 sigma. And we know from the empirical rule that approximately 95% of the data lies here. So longer than 500. And because this is a symmetric distribution, I'll have 2.5 here and 2.5 here. So the answer would be approximately 2.5% of bulbs could be expected to last longer than 500 hours. Another question, distribution A, distribution B. Value from distribution A is 50,000. Value from distribution B is 40. Convert each value to a standardized Z value and indicate which one is relatively closer to the mean, to its respective mean. So we can use the standardized value to compare when the means are different. Okay, so we can use it like similar to coefficient of variation to compare two distributions when the mean, two values when the mean is different. Okay, so if you find the Z value of the first number, Z of the first number, which is 50,000, you subtract, because it's from distribution A minus the mean, over 6333, you find the answer. And for 40, you subtract from its mean, which is 33.4, and you divide by 4.05, and the one which is less than the other would be closer to the mean. If Z is 1, it would be closer than 2, closer than 1.5. So you evaluate the results and mention which value is closer to the mean. IQ scores have a distribution thought to be bell-shaped with a mean equal to 100, standard deviation 15. Suppose a person has IQ 121, calculate the standardized IQ. So 121 minus 100 over 15, and this would be your answer. We end up with the last exercise. The average of 60 students, number of students is 60, attended quiz 1 in Stat 101 is 75%. So this is the average, okay, 0.75, and the variance is 0.16. Sorry, this is the variance. Pay attention. The variance, it is sigma square, okay? So to find the standard deviation, you find the square root of 0.16, 16%, and square root would be 0.4, okay, 0.4. So the standard deviation is 0.4. Now the question, if your Z-score is 0.024, so this is your Z-score, okay? What was your score in the quiz? So Z is given, and he asking for X. He's asking for X. Well, X is not known, but we can find it using this formula. So X would be, if you cross multiply, 0.4 times 0.024 plus 0.75 will give you the answer. So 0.4 times 0.024 plus 0.75, your answer is 0.7596. Okay, so this is your score in the quiz. I stop here, and if you have any question, please feel free to ask.